You aren't as special as you may think, and I'm not getting biological or even philosophical. What I'm really talking about are birthdays. Here's a question. How big do you think a group would have to be for there to be at least a 50% chance that at least 2 people share a birthday? Only 23 people. It seems pretty bizarre, but really, it just comes down to probability. All probabilities lie between 0 and 1, with 0 representing an event that is completely impossible, such as traveling faster than the speed of light, and 1 representing an event that is certain, such as rolling a number between 1 and 6 when using a standard die. Anything in between is fair game, with the probability of flipping heads with a coin being 0.5. In math, the probability of a given event occurring is equal to the number of ways in which the event can occur over the total number of possible outcomes. So, for example, the probability of this little guy randomly choosing a burger is 2 over 3, since there are 2 burgers and 3 items in total. Now that we got that down, let's get into some key assumptions about the birthday problem. Firstly, we assume a year to be 365 days, so no leap years. Next, each birthday should be equally likely, so it's not like July 23rd as a birthday is any more likely than December 23rd. And lastly, no twins, since the birthday paradox assumes only independent events, especially because the point of it is to determine the probability of a birthday match in a random group of people. This wouldn't work with twins since the occurrence of concurrent birthdays would be a dependent event. Let's reconsider our group of 23 people. The probability that 2 or more people could share a birthday would be equal to the probability that 2 people in the group could share a birthday, plus the probability that 3 people in the group could share a birthday, plus the probability that 4 people in the group could share a birthday, adding all the way up to the probability that 23 people in the group could share a birthday, which is a lot of unnecessary calculations. But we can be smart about the way in which we calculate this by using a few tricks. If 1 represents an event that is certain, this would simply be the sum of the probabilities of all possible outcomes, since they should all add up to 1. Then we can subtract the probability that no one shares a birthday, or the probability that everyone has a unique birthday, which is the outcome we don't need, in order to find the probability of the remaining cases, which is the probability that 2 or more people share a birthday in our group. Calculating the probability of everyone having a unique birthday is much simpler. For the first person in the group, the probability of them having a unique birthday is 365 out of 365, since they kind of get first dibs on whichever birthday they want. For the second person, the probability of them having a unique birthday is 364 out of 365, since one day is already taken by the first person. Following similar logic, the probability of the third person having a unique birthday is 363 out of 365, and so on. We continue this until we get to the probability that the 23rd person has a unique birthday, which is 343 out of 365, since 22 birthdays are already taken. Multiplying this out, we get approximately 0.492702767. Now what we can do is plug in the value we just obtained into our previous formula, subtracting it from 1, which gives us approximately 0.507, or 51%. So why is it a paradox? Well, firstly, we're bad at math. You're probably like, me? Yeah, you. In fact, all of us are pretty bad at math. We can intuitively understand linear functions, however, the human brain cannot truly comprehend the computing power of some more complex functions. With this visual, think of the vertices as the individuals in a room, with the lines between points being the opportunities for possible birthday matches. In a 23gon or an icosahedron, though there are just 23 vertices, there are so many possibilities for 2 people to share a birthday when there are 23 people in a room. And the chances of there being a birthday match just continue increasing exponentially as the number of people in a room increases. Secondly, we're really self-centered. We tend to think of ourselves first, and I barely know the birthdays of people I know. So even if you may not share a birthday with someone else in a room, there's a very high likelihood that someone else does. Now, no matter whether you enter a classroom or your workplace, just know that it is very likely that someone out there has a birthday twin, even if you don't. Now go out there and flex your probability powers.